The James Webb telescope shakes up our preconceived ideas. It has already detected a whole series of cosmic systems that are far too large and massive for their initial development. This raises a crucial question. If we are already wrong in our models of early universe evolution, could we also have misunderstood the beginning of the universe? Although the theory of the Big Bang has long been accepted, it is currently the subject of growing study. Is it conceivable that the Big Bang was not the beginning of everything, but simply one of many infinite cycles? In this context, the next intriguing question is not about the middle, but what actually existed before the Big Bang. Our entire universe was hot and dense, and then nearly 14 billion years ago, the expansion began. Fans of the cult series, The Theory of How Things Came to Be, are not the only ones aware of how the birth of the universe unfolded. According to our current knowledge, the Big Bang, often cited, describes the event during which space, time, and matter emerged from an original singularity around 13.8 billion years ago, paving the way for everything that exists today and will exist in the future. So far, the world agrees. But how can we know today what happened no less than 13.8 billion years ago? It's very straightforward in hindsight, a development that began with the Big Bang and continues today. As we know, the universe is not a rigid and unchanging entity, but a constantly expanding development since its creation. For a better understanding, it is important to clarify that the universe is not expanding into an existing space, but that space itself is constantly expanding. And if we trace the universe's expansion in time using Einstein's general theory of relativity, we eventually reach a point where the density of matter and energy is infinite, and where all spatial distances are null. We have thus returned to the hot and dense state described by the Big Bang theory. However, theoretical calculations are not the only factor that allowed the Big Bang theory to occupy a dominant place. There is also the cosmic microwave background radiation. This is radiation in the form of microwaves that was created about 380,000 years after the birth of the universe, and which still fills the entire universe today. Since this radiation was theoretically predicted in the Standard Model, its detection is considered essential proof of the Big Bang theory. But despite all the mathematical models and remnants of radiation found, we must not forget that the Big Bang also raises many questions to which it does not provide answers. For example, according to our knowledge, the primitive universe must have undergone the first great growth spurt in a fraction of a second, expanding by a factor of 10 to the power of 30 to 10 to the power of 100 in an incredibly short period. However, the question of how this cosmic expansion occurred and whether it really took place is as dark as the following question. Was there anything before the Big Bang? In fact, the Big Bang theory cannot solve all cosmic mysteries. For instance, the question arises as to what really happened in the background of the birth of the universe. In other words, what allowed something to emerge from nothing 13.8 billion years ago? Was there a triggering element, or was it just an absolute coincidence? And how can matter arise from nothing? Stephen Hawking addressed this complex subject in a straightforward and logical manner. The genius who passed away in 2018 was quoted as saying that asking what was before the Big Bang is as pointless as asking what is north of the North Pole because time itself began only with the Big Bang. It is an event that could not have been caused by anything or anyone. The laws of nature themselves tell us that the universe could have come into existence without the need for energy or a cause. However, other researchers have issues with this hypothesis, but we will come back to that in a moment. The question of why matter and radiation are so uniformly distributed in the universe is no less controversial. No matter where or at what distance we look on a large scale, galaxies, gas nebulae, and radiation always show similar densities and distributions. The current explanation is based on the state of cosmic expansion, but some specialists propose that this process continues today and that a huge number of parallel worlds have formed over time. The theory of the Great Rebound comes in as a provisional conclusion. One could argue that despite its popularity, the Big Bang is still contested and that we are still in the process of deciphering all its aspects and consequences. Thus, over time, options have emerged that attempt to explain the beginning of the universe in completely different ways. And even though the corresponding theories sometimes differ radically from one another, they have one fundamental point in common. We must abandon the idea that the Big Bang was the beginning of everything. If another universe existed before the Big Bang, it was simply the hazardous change from one universe to another, and it would therefore be better to describe it as the Big Bounce. But what exactly does this mean? Are there unmistakable signs that confirm the existence of such a cyclical universe? In principle, the idea of interaction between annihilation and rebirth is not new. The early Indian Vedas, for example, describe the universe as a sequence of creation, annihilation, and recreation that repeats infinitely. The Mayans had a very similar worldview, and Einstein himself considered the idea of an oscillating and cyclical universe, which he thought was indeed conceivable. In accordance with the saying, what expands can also contract again, cyclic models are now very popular in cosmology. It is not surprising because this approach allows us to circumvent the problem of causes. If matter has always existed in an eternal cycle, the question of how something can arise from nothing no longer applies. In such a context, absolute nothingness simply never existed. In this case, the strange uniformity of the universe could also be explained by cosmic withdrawal, which evenly distributes matter. The trigger for the Big Bang would also be easy to find. It would simply be the end of the previous cycle, followed by a new stage. The expansion of the universe could therefore be straightforward if it weren't for the problem of entropy. According to the second law of thermodynamics, the degree of disorder in a closed system always increases, which also applies to the universe. Due to the continuous cycles, entropy should therefore increase indefinitely. This means that with each new cosmic beginning, a little more radiation is created compared to matter, and the universe will eventually reach a state of maximum entropy where neither atoms, stars, nor universes can exist. However, this is not the case due to the entropy problem. Furthermore, disordered particles would be compressed with each contraction of the universe, while the following new beginning would be accompanied by an even greater scattering of energy. Conversely, this means that each new cycle would last a little longer than the previous one. However, in the traditional sense, it would also mean that the cycles get shorter and shorter as we go further back in time. And, as in the theory of the Big Bang, we would eventually arrive at a starting point where everything is concentrated. Should we then reject cyclic models altogether? After all, the corresponding theories explicitly exclude a primitive initiation of the universe. We should not dismiss the idea of an eternal cycle so quickly. Indeed, scientists have found a way to solve the entropy problem, and what is needed is a universe suffering from a severe form of memory loss. To understand what this means, we need to take a brief detour into the world of loop quantum gravity. According to this theory, and contrary to Einstein's assumptions, space-time is not continuous but divided into small indivisible units. The eponymous loops have a length of 10 to the power of negative 35 meters, which corresponds to Planck length and thus to the smallest conceivable unit in quantum theory. Collectively, the loops interconnect to form the basic structure of the universe, with particles representing the nodes of the network. Thus, we can imagine the universe as a single, constantly evolving web of minute associations that are neither visible nor effective for us. In this context, the original singularity of the universe cannot have existed. Loop quantum gravity only allows for finite values for densities, meaning that infinite density is not acceptable. At the same time, this creates a non-less spectacular event at the moment of the Big Bang. Gravity is reversed. Instead of exerting an attractive force as usual, it repels in an overturn. As a result, space is practically inverted, which has astounding consequences. Consequently, the loop model literally states that the Big Bang was not the beginning of everything. Unlike the theory of relativity, it also provides valid mathematical results before the Big Bang. There could therefore have been a large collapse, in which a precursor universe collapses on itself, and is then pushed back to larger scales by the anti-gravitational effect of its own microscopic network. The resulting fluctuations in matter and energy density destroy all the information of the previous universe. In other words, each new universe suffers a severe loss of memory, which solves the entropy problem, as it is virtually reset. The universe can cut its old ties to entropy and start anew, effortlessly. And now, don't hesitate to click on the like button and subscribe. Become a member of our community, and never miss a new video from us. Until next time.